Hello, my name's Neil. This is my final project for Engineering 253. This video can be used for any purposes Clark College sees fit, and of course, can be made publicly available. My project is called Follow the Light. It is a stepper motor driven solar tracking system, and as I pan over the entire project here, note some of the more obvious features. It has a ball gear and a monopole, which allows for the ball to be rotated to any position. Has two NEMA 17 stepper motors, and with those it has two A4988 motor drivers. It is run on the Atmega 328P microcontroller chip, which is also found in your typical Arduino Uno. And this project, of course, is a continuation of a prototype that I originally developed during Engineering 252. And so it does represent a complete redesign of the mechanical, the electrical, and all the control systems. But before we get there, of course, we're going to go over each part and let's talk a little bit about how I got here. The purpose of this project is to create a platform capable of automatically tracking the brightest available light source. The idea, of course, is pretty straightforward. By placing light sensors around a solar panel, the controller can compare the amount of light received from different directions and then determine which way that panel should move. So if the panel continuously adjusts itself to face the brightest light source, it can then maximize the amount of energy collected throughout the day. The original prototype successfully demonstrated this concept, but it also revealed several significant limitations that motivated a complete redesign for it. The original version used an Arduino Uno, 4 light sensors, and 2 SG90 servo motors. These motors were then mounted in a traditional pan and tilt configuration, just like what you see here. While the system was capable of tracking light, the servo motors quickly became the weakest part of the design. As additional weight was added to the platform, the plastic gears inside the servos repeatedly failed. And additionally, the design relied heavily on commercially available parts that were just never intended to necessarily work together. So that required sanding, modification, cutting plastic, and making adjustments just to assemble the system together. These issues, of course, led to several important design conclusions, and it ultimately is what drove the redesign for this quarter. One of the first major redesign decisions involved replacing the servo motors. Initially, I had considered simply purchasing stronger servos. However, once the cost of high torque servos approached $15 to $25 each, stepper motors and other potential motor options became an attractive alternative. I looked into different stepper motors, and the NEMA 17 stepper motors offered several particular advantages. First, they provided significantly greater torque. They had much better positioning precision, and most importantly, they had stronger holding force with their continuous rotation. So, unlike servos, they are not limited to 180 degrees of movement. This additional capability then, of course, opened the door for a completely different mechanical design. Another major objective was reducing dependence on the complete Arduino Uno board. During development, I realized the majority of the Arduino's functionality comes from a single Atmega 328P microcontroller. This inspired me to build my own standalone controller, and the first prototype was a small proof of concept board that provided only the minimum circuitry needed to operate the microcontroller. After validating that concept, though, I designed and soldered a larger board that included the 16 megahertz crystal oscillator, the reset circuitry, and access to all the analog and digital inputs and outputs. By the end of the project, the Arduino Uno served primarily as a programming platform, something that I could put the chip into and flash a program onto that Mega, and then take the Atmega chip to put into my project. While the custom Atmega 328P board became the actual controller for the tracker itself, of course, there were more things that I had to do than just have the Atmega run those motors. Developing the electronics turned out to be one of the more challenging aspects of this project. After soldering several prototype boards, including both controller boards and stepper motor driver interfaces, I also invested in a desoldering gun, which became extremely useful whenever modification or repairs were required. And I can't say how much this improved my process and made it faster. Of course, as I was getting used to soldering and needing to get better and better with just practice, I was able to undo some of the worst mistakes that I had made. But I can also see myself repairing professional equipment using this desoldering gun as well. So I definitely highly recommend adding this to your toolkit. Several Atmega microcontrollers were damaged during the development, most likely due to voltage related mistakes while testing new circuits. At one point, a digital pin on the original Arduino just stopped functioning correctly, which required extensive troubleshooting. It took a while to be able to find that one. But although these setbacks did consume considerable time, they also provided valuable experience in debugging the electronic equipment. Stepper motors require dedicated driver circuitry. My first solution was to solder my own interface board around the 4988 stepper driver, and while it functioned correctly, troubleshooting became increasingly difficult as more sensors and wiring were added. So eventually I transitioned to a commercially available A4988 carrier board that included integrated sockets and onboard micro-stepping switches. These switches control the MS1, MS2, and MS3 pins, which are short for microstep, and they allow different stepping resolutions to be tested very quickly. This proved extremely useful during development and, of course, ultimately led to the selection of 1/16th microstepping for the final product here. The largest redesign effort focused on the mechanical system. Rather than continuing with the traditional pan and tilt arrangement, I decided to investigate a spherical mechanism. The design consists of a large ball gear supported inside a matching hemispherical cup, and a monopole gear engages the teeth on the surface of the ball, allowing motion to be transferred to the two orthogonal axes. To create the required parts, I used a program called OpenSCAD, which is a script-based CAD program. It is free and free to use, but it is based off of coding. So unlike traditional CAD software, OpenSCAD generates geometry through code alone. This allows dimensions and holes, sizes, motor mounting locations, things like that to be quickly adjusted, so long as you are comfortable with coding. After completing the CAD design, the parts were manufactured using a 3D printer. The final assembly required approximately 800 grams of filament and roughly 53 hours of printing time. Now, it is worth noting here that I didn't print everything that I had wanted to begin with this project. I had wanted to print the whole encompassing outer area as well, but due to time constraints, I could really only get the main part of this system. Because of the long print durations, design decisions had to be considered carefully before committing to the final fabrication, of course. This might not be typical if you have your own 3D printer or if you have a bit of an unlimited supply of filament or maybe a little extra time. It's part of an iteration process to get this even better as well. So it could have definitely served me to have just a little bit more time to be able to function on it. But the resulting assembly successfully integrated the motors, the spherical gear, the support structure, and got the tracking platform into a single system. So now to briefly demonstrate the operation of the system, you can see that the 4 sensors are continuously monitoring light intensity for the left and right, for the upper and lower directions. So when one side receives more light than the opposite side, the controller commands the appropriate motor to move. The movement continues until the sensor readings become balanced again, and this allows the platform to automatically orient itself towards the brightest available light source. The redesign successfully achieved most of the project's primary objectives. The custom Atmega 328P controller operates independently of the Arduino Uno. The 4 sensors successfully control 2 stepper motors. The A4988 drivers provide smooth and reliable motor operation. The spherical gear concept functions pretty well as intended and demonstrates two-axis motion. And the 3D printed assembly successfully integrates all the major systems into a single platform. But several challenges do remain. The D-shaped mounting hole in the spherical gear was printing slightly off-center. This causes the distance between the monopole gear and the ball gear to vary during rotation. And as a result, gear engagement is not perfectly consistent throughout a full revolution. Additionally, physical interference between the motor and support structure limits the available range of motion. To compensate for these mechanical limitations, software motion limits were implemented for now. But of course, with better printing and getting this a little bit more in line, even those coded limitations can be removed. Future development will focus on three major areas. First, the spherical gear assembly should be redesigned and reprinted to improve alignment and eliminate that eccentricity. Secondly, the motor mounting structure should be modified to increase mechanical clearance and expand the available range of motion. Third, I would like to complete the integration of the solar charging system. This subsystem, of course, uses solar panels. It goes to a Schottky diode, which makes sure that power goes to the charger but doesn't come from the battery back to the solar panel. It goes from the Schottky diode into a TP4056 charging board, which then plugs into the 18650 battery. Although the charging architecture has been designed and the components have been acquired, comprehensive testing remains for future work. This project provided valuable experience in embedded systems, motor control, electronic design, additive manufacturing, software development, and engineering troubleshooting. More importantly, it demonstrated that the engineering design is an iterative process. Many of the most important lessons came not from that initial success, but from the redesigns, the failures, and the headbanging along the way. The final result is a significantly more capable solar tracking system than the original prototype, and it provides a strong foundation for a future possible development. I thank you for watching. Have a wonderful day.